lots of exciting news to share today, including new releases and also some introduction about the recent benchmark we did. So first of all, let's quickly go through a quick introduction of Apache Sedona for folks who are here first time. Sedona is now the most popular open source cluster computing engine for geospatial data of any scale for both big data and small geospatial data. And our website is at sedona.apache.org. We also have our code open sourced at Apache Software Foundation on GitHub. We have our X account and also LinkedIn account. So be sure to follow us on social media to get the latest news. Sedona so far has lots of users in different industrial sectors, including logistics, financial services, real estate, public sectors, agriculture, and technologies. The total downloads of Sedona has exceeded 65 millions, and we are observing 200% growth year to year. On GitHub right now, we have over 150 contributors. And Sedona right now support a number of different engines with also it has a few sub projects. So if you want to use Sedona to do batch data processing, you can use Sedona on top of Sedona Spark and also Snowflake. If you want to do stream data processing, you can run that on top of Flink. We have Sedona Flink. If you have very small data, you can actually have we have a sub project called SedonaDB. It is a new sub project we announced last year. It is single node. It is self-contained. You don't have to actually install anything other than SedonaDB itself. We also have another sub project called SpatialBench, which is a benchmark that is used to benchmark the performance of spatial query engine. So we're going to cover all this project today. So here is a quick overview about the Apache Sedona project itself. In particular, this chart, this diagram is about the distributed engine of Apache Sedona. So Sedona has basically three layers. Spatial query processing layer. It has spatial SQL, Python, and Scala API. Also, it equips with a number of distributed query algorithms. Also, it has a spatial query optimizer that automatically chooses the best query algorithms given a particular query. And the second layer is what we call distributed spatial dataset layer. So this layer has a spatial partitioner, spatial index, and data serializer that actually partition data across machines in the cluster. And finally, all these layers runs on top of a couple different distributed engine, including Apache Spark, and Snowflake for batch processing, and Flink for stream processing. By far, our support on Spark is the most comprehensive one. As I mentioned before, we also have a new sub-project called SedonaDB. So SedonaDB is the first open source single node spatial analytics engine that treats geospatial data as a first-class citizen. And Dewey going to cover those later on today. But in particular, SedonaDB, as I mentioned, is single node. It also uses columnar in-memory dataset layout. It has spatial query optimization and the spatial query processing layer as well. And we are adding lots of raster functions. So if you are close to the development, if you see our GitHub repository, right, you probably will see that we are already adding lots of raster functions there. And here is a quick start of Sedona. So just in case you want to try it out today. So the easiest way to try Sedona as follows. So first, if you want to try the distributed engine on Sedona, you can try Sedona Spark in a Docker container. We have a Docker image published under official Apache Software Foundation account. You can find it on Docker Hub. So just search Sedona. Apache Sedona there. You can put the image there, and you can run that Docker image. It will give you a Jupyter Notebook interface. Also, it also gives you a Apache Zeppelin notebook to allow you to create charts in a web notebook. Another easy way to start Sedona is through SedonaDB. As I mentioned, it is a single node engine, it's self-contained. You just need to do pip install Apache SedonaDB. And after that, you just import and you can then directly execute query right away in your Python shell. In terms of releases, Sedona follows the 3-month release cadence. So basically, we publish a new release roughly every 3 months. In 2025, we published almost 4 releases. So 171, 172, 180, and last week we published the latest minor release, maintenance release, 181. So here is the agenda today. So first of all, I'm going to quickly go through the community growth we observed in 2025, which is very exciting. And we're also going to talk about the new releases, Sedona 181, and also SpatialBench 0.10 release. And we also going to talk about our recent response to the Databricks blog post about Sedona performance. And finally, Sedona committer Dewey going to talk about SedonaDB 0.2 release, which is the latest release of SedonaDB. So in terms of community growth, in 2025, we observed significant growth in the community, both in the development activities and also the downloads. So there are a couple new committers and contributors join the project, including a few new committers, Pranav, Peter, and Dewey. Thank you all for contribution. And we also have a new PMC member, Feng. And we also have a number of new contributors participate in the project in the year. First of all, in the open source Sedona GitHub repository, which is the one for Sedona Spark, Sedona Flink, and Sedona Snowflake, we have 27 new contributors, right? So that's what's bring us to have over 150 contributors on GitHub. And 46 people contributed to Sedona in 2025. In total, we have 155 contributors on GitHub for Sedona Spark, Flink, and Snowflake. For SedonaDB itself, SedonaDB sub-project has 26 new contributors in 2025, which is great given that this is a brand new project we just announced in September. We already have 26 new contributors. And for SpatialBench, we have 8 new contributors in 2025, which is also great. And the adoption of Sedona continued to grow. So the total downloads of Sedona is more than 65 million. The monthly downloads of Sedona is more than 2 million. And the commit activities increased from over 1,500 commits in 2024 to over 2,000 commits in 2025, which is very exciting. All right. Now let's talk about Sedona 181, which is the new release we have. There are a couple exciting features, but today I'm just going to cover 3 main things I think that are very exciting and very interesting to talk about. So the Sedona Flink SQL module, STAC authentication support, and also the 2 interesting new SC functions we added. So first of all, Sedona Flink SQL module. In the past, before Apache Sedona 181, if you want to use Sedona Flink, you first need to create Sedona context in either Java or Python. And you're going to create Sedona context on the Flink table environment, right? So this was great, but nowadays many people use Flink in like you use some sort of fully managed Flink services such as Confluent or Wavarika, right? So in some of those offerings, they do not allow users to use languages other than SQL. So in that case, if we ask the user to always create Sedona context, then that they won't be able to enable Sedona, right? So in Sedona 181, we added pure SQL support for Sedona Flink. That means starting from 181, you can actually use enable Sedona Flink in pure SQL without using any Scala Java Python code. It is fairly simple. In your SQL sentence, you just need to use, of course, you need to install the jar of Sedona Flink, right? But after you put the Sedona Flink jar in place, you just need to use load module Sedona. And if you no longer need it, you can just use unload module Sedona. So once you call load module Sedona in the next SQL sentence, you will be actually able to run the following SQL queries: select area and also stgeom from text. This will work out of the box. Boom. This is Sedona Flink SQL. Another new feature we introduced in 181 is the STAC catalog authentication support. Many of you probably are already familiar with STAC. Basically, STAC represents spatial temporal asset catalog. So STAC oftentimes allows you to read the raster data. It is a catalog service standard. It allows first of all allow data vendors to publish and host raster data set, and our STAC data source in Sedona allows you to read those data directly into Apache Sedona raster data tab. It has been working fine in the past, but we also noticed that many STAC services require authentication to access their data because this data, they are proprietary. It is only for their paid customer. So in that case, the STAC catalog and the STAC client needs some basic authentication support. So this support has been added in Apache Sedona 181. And we offer three options. So first of all, the basic HTTP authentication, and secondly, bearer token authentication and the custom headers as well. Here are some examples down here. So these are the example using Sedona Spark stack pattern client. This is API compatible with PyStack client. So if you have been using PyStack client before, you'll be able to do the same using Sedona Spark Stack client with the same API, but what it gives you is a Sedona data frame and with geometry and the raster data type in that. It is pretty simple. If you want to have basic authentication, you just put your API key there, and you'll be able to search those stack catalog. You can also put your bearer token there. Cool. Another feature. So we have added a couple new ST functions in Sedona 181. But in particular, I think there are two functions are very worth mentioning here. They are very interesting. And also those are the first, I would say, computational geometry functions added in Sedona. So they allow you to do lots of very interesting things for some very messy geospatial data. So the first function is called ST approximate medial axis. The second one is called ST street skeleton. Those are already available right now. So if you just look at name, probably it is a bit hard to imagine what they are. But if you look at this chart on the left, so suppose the original data is a polygon, right? So in this particular thing is a polygon with a shape T. So the the boundary of this polygon is actually the blue, has a blue borders, right? Now what this function gives you is the orange line in the middle here, right? It is a center line, follows the polygon shape, right? Of course, this function allows you to adjust some parameters, right? But essentially, this is what it gives you. So, by name, this function computes the medial axis center line of a polygon. Each point on the axis is equidistant from two or more boundary edges. And I'm going to later on give you some example and to show you how that works in reality, in real world use cases. Another similar functions, straight skeleton, right? So by name, it computes the straight skeleton by shrinking polygon edges inward. The result is a tree-like structure useful for root construction and shape analysis. So again, in this case, the polygon shape is the blue boundary, right? And the straight skeleton is a red one. So how are these helpful in use cases, your real world use cases? So here is an example we recently encountered when we developed those functions. That's also one motivation why we added that into Sedona. So if you look at the road network on the left, right? So we actually have a machine learning model, in particular computer vision model, that actually can detect road network from the from satellite images. So this is basically a remote sensing use case. So what it gives you, what this model gives you eventually, is what we call initial vectorized result. So it gives you the road network, but out road network, if you take a closer look, they are all polygons. They are polygons. They are not actually line segments, which are ready for analysis, right? So what you're going to do is that, so the initial vector result directly coming from the computer vision model is very messy. You want to simplify the vectorized result. So basically, smooth the edges of those polygons, right? And after you simplify the vector result, now you want the real road network. So in order to get the real road network, in this case, you will need the medial axis function. So what it gives you is that it converts the original polygon by inferring its medial axis. It basically use the approximate medial axis of those polygons serve as the center line of the road network. In this case, you'll be able to construct a new road network. So this is essentially how people get polygons out of those satellite images. Here is another use case. So this is also another road network we obtained from the computer vision model on satellite images. And this polygon is even more complicated. And you will see that the original polygon from the machine learning model is pretty rough. And you will need to simplify the polygons a little bit. So you get some road network like this one, right? So this is a zoom in version of the image. And then you run the ST approximate medial axis function on that. You get accurate road network from this image. That's how you construct neural network for a brand new area. Cool. That's about the new release, Apache Sedona 181. I also want to briefly talk about another new release we have, which is a Portman release for SpatialBench. As I mentioned before, SpatialBench is a benchmark we designed for assessing geospatial analytics query performance. So we mentioned this a couple times last year in our community office server. SpatialBench has a couple components, including data model, data generator, spatial queries, and also results. So I won't repeat every single thing today, since we covered that a lot last year. But in particular, I want to quickly revisit the query result we had last year. So we used the initial version of SpatialBench we use that and compare the query performance of three open source framework, SedonaDB, StackDB, and GeoPandas. And the results are listed on the right. So we did that on SpatialBench scale factor 1 and scale factor 10. Scale factor 1 is equivalent to around 1 GB data. Scale factor 10 is 10x on that, which is equivalent to 10 GB data. And we have 12 queries in SpatialBench. As you see here, SedonaDB has the best performance. It works on all queries, and it has the best performance in almost all queries. So we recently published SpatialBench 0.1 release to both PyPy and quiz.io. So in particular, this is the SpatialBench data DBGen, which is the data generator. So the query is already published on SpatialBench website and GitHub repository. But the DBGen, the data generator, is a real program, right? Many people will need that to produce the input data of those queries. So we publish that to PyPy and quiz.io. Here is how to use that. You can do pip install SpatialBench CLI, or you can download from quiz.io, which actually you will need to compile that on the fly. And here are some basic usage of SpatialBench database generator, DBGen. You can choose different scale factor. It will, for example, if you choose scale factor 1, it will generate 6 Parquet files, trip table, customer table, driver table, vehicle table, zone table, and building table. All the tables, they are actually in compressed Parquet format. Another thing I also want to mention here is our response to the Databricks blog post before the new year. So some of you probably have noticed that Databricks published a blog post before New Year comparing open source Apache Sedona performance against their closed source DB SQL engine, right? And claim that you'll see up to 17 times faster performance compared to classic cluster with Apache Sedona installed. So this blog post, if you haven't seen that or have seen that, so in our opinion, it is not true, because this blog post doesn't talk about cost, and they compare us open source Sedona against a closed source Serverless SQL engine, which doesn't disclose how many CPU cores and how much hardware are used in the benchmark, meaning that you can compare like 1 CPU core against 1,000 CPU cores without knowing the hardware, right? So this is doesn't tell you the actual cost, and also it is an apple to orange comparison. So in order to ensure a fair comparison, the Sedona community, we actually did a benchmark, and we already published that on Sedona blog post. So if you are interested, be sure to go to Sedona website and go to the blog post section and read this blog post. And in short, we compare classic Databricks jobs using a free and open source Apache Sedona, and compare that with Databricks closed source Serverless SQL engine, right? But we normalize on dollar cost. That means we don't have to know the exact hardware. We just need to see how much you pay per query using Apache Sedona and Databricks Serverless SQL. To compare the performance and to make sure the query is reproducible, we use SpatialBench, which is designed to handle such use case. So here is the result. So first of all, if you look at the SpatialBench query result here, right? So we have 12 queries, and we did that on scale factor 100 and 1,000. You can see the status of all the queries, right? So the green mark means that this engine can finish in a reasonable time. And if you see a timer here, meaning that this query timeout. So it keeps running until the timeout time up. And a red cross here, meaning that this engine cannot finish. It arrows out either out of memories or something else, right? It cannot finish, it arrows out. So based on that, here are the numbers, right? So if you look at numbers, the way to look at that is we use the Sedona cost. We use the Sedona cost as the uh, uh as the base as a one, and we use Serverless SQL to compare to that. So basically, this shows you how essentially tells you how many times Databricks Serverless SQL is more expensive compared to open source Sedona, right? So the chart above is for scale factor 100. The chart below is for scale factor 1,000. So if you look at the first chart here, first of all, lower is better. So the purple bar is Sedona, and the red bar is Serverless SQL. As you see here, the so-called 17x faster performance is just not true, right? Because you don't tell us the cost, you don't tell us how much hardware you use, right? You might end up comparing one CPU core with 1,000 CPU cores. So you'll see that in most of the cases, Serverless SQL is way more expensive than open source Sedona. And also it is less capable compared to open source Sedona because it finish less queries compared to Sedona. So this pretty much our response to the Databricks blog post. And now let's talk about SedonaDB, which is our new single node analytics database engine with geospatial as a first class citizen. And in particular, we want to talk about the new release, 0.2 release of SedonaDB. Now, let's invite Apache Sedona committer Dewey to talk about that, since he has been leading this project. Let me promote Dewey to the panelists. And by the way, folks, during the community office hour, if you have any questions, feel free to post in the chat, right? And also can ask Q&A. So we're happy to answer that. Dewey, can you take over?
Hi, yeah. Let's so you have to unshare your screen, I think. So let's pop open this guy. Does this look like SedonaDB to you?
Yeah.
All right. Yeah, so I'm just talking about latest SedonaDB release. There's a blog post that has this is like a sort of a ripoff of the blog post that we wrote, sort of announcing the release. Um, and yeah, these are sort of fully rendered, but I'm going to tape them out to you because one of the cool parts and one of the things that I'm the most excited about with SedonaDB is that you get some autocomplete to help you do spatial stuff. And that's like one of the best parts about a GeoPandas experience is like you get autocomplete and inline documentation to help you. And that's what we're trying to bring to the sort of different idiom where you're lazily evaluating the stuff and collecting it at the end. So yeah, here we are. This is what you can do to install the new release. This should work. And I'm going to turn on the interactive mode, which is print stuff by default, because I'm not doing anything expensive that will cost a whole lot of money. So yeah, the first thing that we're going to do that we did, the real big thing that I was excited about was reading GDAL sources. So this means shape files, anything that PyOGRIO can read, which is what backs GeoPandas. We are quite literally using another Python package to do this. We're able to hook in at a non-Python level. So we don't have to deal with Python performance issues, but we do get the benefit of using the same engine that GeoPandas is using to read these files. So to make sure that I highlight that we're actually using that engine, which I think is very cool and also points people to that engine if they have questions. we can read those files, and you get nice autocomplete to kind of help you out with that. This happens to be, oops, this happens to be the state of Vermont. You can do like 2 pandas plot. This is kind of one of my favorite things to just real quickly look at what am I even doing here. Yeah, and this this works with read IOGIO. This also works with zipped things. So like this is using GDAL infrastructure to deal with this, but you can deal with a zip shape file. And my sort of favorite example is like you can also just do URLs. One of the cool things about some of these formats like flat GeoBuff is that they have super efficient spatial indexes embedded in them. A shapefile the same way. And you can, if you're querying using a st-intersects or like a join and then an st-intersects, Data Fusion and SedonaDB are great at sort of making sure that this st-intersects query makes it all the way down into the scan. So when we're scanning this flat GeoBuff file from the internet, which is huge, it's like many gigabytes, you actually don't, it only takes like half a second. You don't have to do anything because it only is able to read a very small amount of that file. So yeah, basically you can read GDAL. This dovetails very nicely into the next thing that we implemented, which was writing GeoParquet 1.1 files. GeoParquet 1.1 is the version of GeoParquet that Overture uses. And the Overture Foundation was instrumental in actually making sure that the GeoParquet 1.1 happened because it made so much improvement for partial reads. So if you have Overture, basically can get away with statically hosting a whole bunch of Parquet files, and we can query them quite easily without downloading the whole data set, just by having a normal query with an st-intersects somewhere in there, or st-contains, or you can basically query the data set a little bit more fearlessly, which is great. So we implemented that read support in the last release. That was right out of the gate, but we can rate these files yet. So if you wanted to, convert some random GDAL source into Parquet, then you can do that. And this GeoParquet version 1.1 will give you this bounding box column, and this is what allows that. Yeah, it's what it allows the scan to be super efficient. One of the cool things that I think that kind of all brings it all together is whoops. RAO is that you can use globs. So like you can, if you've got like, 100 files and you want to just put them all together and then write write this. Whoops, I think I have to give it a name. You can kind of glob together a whole bunch of files and just write them right away. We also implemented the beginnings of spatial sorting. And you have to do it in a bit of a manual way here, and this is on the blog post as well. But you can order by the special function, and it will give you a spatial ordering that makes sense for your data and gives you bounding boxes that make sense to make querying things faster. This was something I'm pretty excited about, and we're hoping to deepen this so that all you have to do soon should be this, ordered by geometry. But at least today, you need this thing to make that happen. Another example, we have implemented a Python UDF thing. This is similar to how like a DuckDB or IBIS, or I think it's a little bit similar to how Apache Sedona, Sedona Spark can do this as well. Our syntax is a tiny bit different for now. Getting the framework together is sort of the important part, or the hard part for me. And then aligning all the syntax is a separate struggle. And I'm totally willing to do it, but somebody needs to ask first because it's a lot of work. But getting all this stuff just to be wired together was my goal for the last release. So if you need to have some shapely function that's not implemented yet, or if there's a combination of operations that is special that you already have wired up in Shapely. Then you can wire that up as a function. You can register it, and you can call it from SQL. And yeah, I also want to highlight a few things that we're working on in the next release of SedonaDB, which should be probably in early February. Yeah, item level CRS. So this is the post just CRS model, where you have every in SedonaDB for the most part we follow the GeoParquet or the GeoPandas model, where every column has its own CRS, and the query planner knows about that. Python knows about that when you're typing the query. So you get better errors sooner, and you get more efficient operations because we don't have to check CRSs for every row. If we have 2 billion rows or something, we're not dealing with CRS stuff for every row. We've pulled that out to the type so that can be dealt with the planning time, and we can plan a more efficient operation by knowing some things in advance. But also, item level CRS is the idioms that are used in Snowflake. I believe that Databricks supports them. The new Spark geometry support will support them. And so, yeah, we have to at least be able to represent that in our engine and be able to get stuff in and out of that format. So this is just a very quick example. Like this is a scalar function, and you can call it on an item CRS. If you call set SRID and you have these things as a column, then you can propagate that information. So like pretty much all the functions by 0.3 should work, including aggregates. And basically it's a pretty trivial mapping for most functions. Like STTranslate, if you give it an item CRS, then it will export an item CRS too, and it will make sure all the CRSs are copied over, which is what PostGIS would give you too. And here's just an example that I put together where I wish that engine supported this. So I was querying a bunch of water quality sites. It's like Canadian water quality monitoring data, and they've got this column datum. So I don't know if anyone has a lot of experience with NAD 27, but it's like the annoying long lat that is not actually long lat. It's like shifted slightly, and converting it to WGS 84 or NAD 83 and making sure that all these sites are aligned is actually kind of a hard problem to do with GeoPandas. Or it's a verbose problem. It's possible, but it's verbose. But this is the kind of query that we're hoping to make sure just works. And we haven't quite implemented all the functions to do that, but we will by the end of 0.3. And I want to highlight some more things that are coming. We'll be able to read Parquet files. The PR that we did into ArrowRS to make this work is now available with our data fusion dependency and our arrow dependency. So we can do that now, and we'll be able to implement that shortly. We have some new documentation, which is exciting. We can have pictures in our documentation, which is great because geometry has a lot of pictures in it, or it's best explained by having a lot of pictures. We've got performance improvements. Every geospec function got a whole lot faster that returns a geometry. STBuffer, I think, was the biggest win, or anything that produces huge geometries. We basically just circumvented GeOS's WKB writer because it was slow, and couldn't be hooked into in the way that we needed it to be hooked into to improve memory usage. Yeah, we were I didn't do it, Peter did. We implemented STBuffer using the geocrate, and that got a whole lot faster. I'm pretty excited about random geometry generation, but I'm probably the only person who is. But that'll get better. I'm also probably the only person excited about our data frame API, but that will also get better. That's kind of why I started it's why I got started in spatial in the first place. So I wanted to make sure that I follow that project through. And there's an exciting PR. Hiroki just implemented STAffine and a bunch of other functions, which are very verbose to implement because they have so many arguments. But they're super useful. Yeah. This is actually a really tiny bullet point that deserves to be in much larger font, but I'm not sure if it will merge before 0.3, but I hope that it does. Larger than memory spatial joins. Kristen opened an issue on the SedonaDB describing how exactly it's implemented, and is PRing that in chunks. He's had a few chunks there already with the improvements to the existing join. and there's more coming. Yeah, we've had a GPU spatial join. Feng has a PR to wire that up. We merged the initial support for that, the C library, C++ library that does that. Liang did that, and it was fantastic. Some of those joins get up to 6 times faster. GPUs everyone thinks that GPUs are not like tricky to implement for analytics because of the cost of getting stuff onto the GPU and off. But spatial is one of those one of the use cases where the computation is so intense that it actually is worth it in a lot of cases. So if you are running SedonaDB on a GPU enabled machine, you should be able to speed up some of your workflows after that merges. And also we had an LAS rudder point cloud stuff PR'd in. I need some tests, and so that might take a while to merge, but yeah, I just wanted to thank all our contributors because I spend a lot of my time reviewing, and it is very cool that I get to do that. In particular, Haruki and Peter have implemented a ton of functions, and I'm going to do a very bad job pronouncing that name. But Avajiva on GitHub did an absolutely fantastic job, implemented a ton of functions for the 0.2 release. Genus also did a bunch. And I also wanted to highlight, oh yeah, JP is just Pavlin. Just did a bunch of PRs as well. Yeah, this is just, I'll paste this on to a gist shortly, and I'll post it in the chat. But this is just some of the data that I used to get started.
Dewey Matt has a question in the Q&A.
Yeah, share a link to the notebook. Yeah, I'll give me a second to paste that into a gist, and I'll I'll get it for you very shortly.
All right. Thanks, Dewey. So, that's all the content we're going to talk about today. And just a reminder, we recently have a new O'Reilly annual book published talking about cloud native geospatial analytics with Apache Sedona. Right now, this book is the ebook of this one is totally free. So if you search online, search this particular name, Cloud Native Geospatial Analytics with Apache Sedona. So we're just going to be able to provide you a free copy. So just search the name on Google, it will give you the download link. And as you know, Sedona is always call for help. First of all, you can contribute to Sedona documentations and also the notebook examples, so other people can reproduce and learn more how use cases you can do using Sedona. And you can also participate in our release test. So this release test tests the correctness of each release candidate before it goes out. And this happens only on our mailing list. So if you want to participate, be sure to subscribe to our mailing list. And the detail of subscription is on Sedona website community page. And you can help us verify signature and perform some basic correctness check. And we also periodically have live stream about Sedona success story. So if you're interested and want to share some cool use case and the examples you developed recently in your life or in your work, you can reach out to me through email, or you can reach out to me on Sedona Discord. So if you haven't joined Sedona Discord, be sure to join us there. We post our recent news, and also our committers and TMC members are very active on Sedona Discord. So I'm going to stop sharing now, and I'm going to stay here for a few more minutes, just in case anyone has a question. Okay. Alex has a question. Let me write down this. So I pasted the the link, the verbose link that allows you to download the free copy of the book. It is in the chat. And Lorena has a question. Okay. Can you share the link of Databricks performance block? Let me do that. So the first block, so this is the Sedona response to the Databricks performance block. The second link, so this is the Databricks blog post. Spatial drawing now 16x faster out of box. It is all in the chat.